Hello, everyone, and good afternoon. Welcome to the NCCR Automation Seminar Series. Also, welcome to our guest. I see quite a lot of new names, so very welcome to this seminar series. Our speaker today is Professor Timm Faulwasser from TU Dortmund. I'll just go through a short introduction, and then I'll leave the stage for Timm for the presentation. So Professor Faulwasser is currently a professor at the Institute of Energy Systems, Energy Efficiency, and Energy Economics at TU Dortmund. He studied engineers cybernetics at the University of Stuttgart, majoring in systems control and philosophy, before he completed his PhD at the University of Magdeburg in 2012. And then he was a postdoctoral researcher at EPFL and Karlsruhe Institute of Technology before joining TU Dortmund in 2019. His research interests are quite diverse, including optimization and control of uncertain nonlinear systems and cyber-physical networks with applications mainly in energy, climate economics, mechatronics, and process control. So thank you very much, Timm, for accepting our invitation, and we very much look forward for your talk today.
Thank you, Wahid, for the kind introduction. Let me share my slides, and I'm happy to see so many familiar faces among the participants, and it's finally nice to have a bit of an audience for presenting during these weird times of a pandemic. So what am I going to talk today about? I will set a kind of an ambitious target for this presentation by attempting to show you some ideas of what could be possible on necessary and sufficient stability conditions in MPC. And in order to achieve this, I will take an optimal control point of view, because as I'll try to convince you, very often when we look at MPC, we do a lot of optimization, we do a lot of control, but we do not necessarily do a lot of optimal control. And I guess to this audience, it goes without saying, all of you know about MPC, a lot of you do research on MPC or have been applying it. And the core idea of MPC is the idea of receding horizon optimal control. So based on a state estimate or a state measurement, you'll solve some optimal control problem, and then you apply the first part of this optimal control trajectory to the system, and you repeat the cycle. And now, depending on how you have learned about MPC, you might prefer the discrete time flavor, or you might prefer the continuous time flavor of MPC. At the end of the day, in terms of the conceptual idea, is very similar in both worlds. And I will today mostly focus on the continuous time point of view. So, but when MPC started roughly in the 1960s with first ideas, then it was literally rocket science. But nowadays it's applied to rockets, namely speaking of the Falcon 9 rocket of SpaceX. The landing of the boosters is done by MPC, but you can find MPC applications nowadays in process control, in automotive, in robotics, in many areas, in energy systems. So it has been and continues to be a huge success, but where did it come from? And if I attempt here a timeline, which as a disclaimer will be incomplete, then the first inceptions of MPC can be traced back to a Russian mathematician named Propoy in 1963, or to the book of Leon Marcus on optimal control. And in the book of Leon Marcus, they explicitly, in one of the later chapters, gave you the following quote, that one technique for obtaining a feedback control out of the Pontryagin maximum principle is to measure the state, compute the open loop control, apply it, and then do it again. And that was expresses verbis how they wrote it down in 1967. Then we have seen a lot of developments. I can't list all of them, and for sure it's not complete, but we have seen a lot of different stability proofs with terminal constraints, without terminal constraints, in the distributed setting, in the stochastic setting, you name it. And lately, about 5, 6, 7, 8 years now, we have been digging into dissipation inequalities or dissipation concepts for optimal control, which has changed the perception. They will play a later role. But even beyond that, MPC continues to be a success story because it's somehow very adaptive to new trends. A lot of the people here in this audience will likely do some research on combining machine learning and MPC or on data-driven MPC. So it has been also a kind of a success story in terms of keeping us busy in academia to reinvent it, to improve it. And now, what am I trying to do here today? If you look at continuous time MPC, and what can we do if we want to analyze it? You have kind of three main routes you can go. You can introduce some terminal ingredients, so terminal penalties and terminal constraints, and try to derive stability conditions on that. You could go with sufficiently long horizons, or you could go with dissipativity assumptions. In any case, whatever option you choose, there are also other variants around there. If you attempt a blueprint of a stability analysis proof, you'll have to talk about 3 to 4 steps. On the top of it, you will talk about, okay, if I do repeated optimization, do I have a guarantee to be feasible in each step? That's the first thing you have to do. Second thing is, and that's what you learn if anyone tries to teach you an MPC stability proof, they will say, hey, you have a natural choice for your Lyapunov function. That's the optimal value function, which assigns to each initial condition of the system the optimal value of the performance index. Then, in one way or the other, you'll have to account for the finiteness of the horizon, because the optimization here is truncated at a finite horizon for numerical tractability. You'll have to take care of for the truncated part, that is for the missing horizon from the end of where you optimized up to infinity. And how do you typically do this? Or the easiest choice is with some kind of upper bound, which we then name classically the cost to go, and which will reappear at some point later. And then once you have done this way of accounting for the finiteness of the horizon or some other way, we'll start to analyze the sequence of OCPs. But that's the blueprint, right? And now what makes it so complicated? Well, you change a bit the structure of your problem, you change your terminal penalty, or you change the set on which your terminal penalty is indeed an upper bound on the cost to go, which typically forms your terminal constraints, then you restart to do the analysis. And this is why there are so incredibly many variants of MPC stability proofs out there, although you can bring them down to a few core ideas. Whenever you change a bit, you can write down a new proof, which is quite fruitful for many PhD students, but also a bit tiring in some sense. And now what I want to aim here is, I want to do an analysis, and I don't want to say, do I have a terminal constraint? Do I have a terminal penalty? And I do not want to make explicit assumptions on their properties or on the structure I impose, not on the level in terms of what are my ingredients for designing the OCP. And once I have found such a framework, I would like to take a look, can I show something like sufficient and necessary conditions for stability or convergence of the closed loop? That's the ambitious target I've set out here for this talk. And how are we going to do this? Well, we will combine optimal control and dissipativity. And for some people here in the audience, they already know this or might kind of have a good guess of the story that comes now. Others here might think like, what the heck has dissipativity to do with optimal control? Well, dissipativity, we all know this, dates back to Jan Willems, the 1970s, around about 50 years from now, and expresses this simple idea that we have a system of input and outputs, that if the system is dissipative, then typically what we want to express is that the change in stored energy is bounded from above by the supplied energy. And then Willems went on to formalize this in terms of either integral or differential dissipation inequalities, where the function capital S of X denotes the stored energy or the storage, and the function W is the so-called supply rate, which describes how much energy in some sense is flying, or abstract energy, over the system boundaries. That's a very classical concept. And why is it so useful? Now, beyond optimal control, so systems in control at large, dissipativity is so useful because you can make use of it in a multitude of situations. Stealing here some overview of a paper of Christian Ebenbauer's from 2009. You all know Lyapunov inequality, differential Lyapunov inequality. You can say this is a dissipation inequality, where here this decay function is your supply rate. But you could as well say, well, if you want to talk about passivity, if you want to talk about L2 gain, input to state stability, minimum phase properties, all this can formalize in the frame of dissipation inequalities. And now what not only me, a lot of colleagues have been adding in the last few years is a stream of analysis which analyzes optimal control problems by choosing a specific supply rate. Namely, the supply rate will be the stage cost of an optimal control problem minus its value at steady state. And this will then allow us to analyze optimal control problems. But before we do this, before I tell you the two important consequences that we need here from strict dissipativity, how could you check strict dissipativity? Again, it pays off to go back to the original work of Jan Willems, because he suggested to look at the amount of energy you can extract from a dynamical system. He coined this the available storage. And if you want to compute the maximum amount of energy you can extract from a system, then what you would literally try to maximize is the amount of minus the supplied energy, which is then the energy taken out from the system, generated by some control function over a free horizon, in a free end time fashion. And if this amount of energy that you can extract from a system is finite, then this is equivalent to saying the system is dissipative with respect to the supply rate W. Now, why do I put this up here? Because this is an optimal control problem. And it turns out that the optimal value function of this optimal control problem, this one here, which we name the available storage, is one of the storage functions for a nonlinear system. So already at the, let's say, creation of the dissipativity notion for systems in control, Willems directly linked it with optimal controls. So it's not so much of a surprise if you dig a bit deeper that both concepts are closely linked. Now, I now want to talk about strict dissipativity in optimal control. And I've started off with such an MPC loop. So I need to strip this MPC loop and just look at the optimal control problem here, okay? And now what I want to suppose or want to assume is that for a certain set of initial conditions in our optimal control problem, a certain dissipation inequality holds. And namely, in this dissipation inequality, what we require is that there exists a storage function whose change is bounded from above by the integral over our supply rate, which is again the stage cost minus its value at a dedicated point, C bar. And then we have an extra term appearing here with a class K function, which looks horribly technical at first sight, but this term does nothing else than rendering this dissipation inequality strict. That means this dissipation inequality has to hold with strict inequality whenever Z star is not at Z bar. And what is Z star? That's just a tuple of the optimal state and the optimal input. I combine them into one vector because this helps us to analyze the problem and helps us to keep the notation a bit more complex. And now the standing assumption I want to make is that along any optimal trajectory I compute by solving my optimal control problem, such a strict dissipation inequality holds. And now you might say, hey, hang on, this seems to be a very strong assumption. Can you justify that this is a reasonable assumption? Or are you assuming something here which is way, way too strong? Well, let's first take a look on what the implications, so I mean the immediate implications, not the far-fetched ones, of strict dissipativity are here. If we assume that this dissipation inequality holds, then you can immediately almost see that this state Z bar is the unique optimal solution to this steady state optimization problem here. Why is that the case? If we are at steady state, these terms here on the right-hand side equate to 0 because the state trajectory doesn't change. I can bring the strictness function to class K function alpha L to the other side. I can drop the integral. And then what says there? Well, that L of Z minus L of Z bar is 0 exactly when Z is at Z bar, and it's strictly positive everywhere else, which is nothing else than saying this Z bar has to be the optimal steady state. And not only a locally optimal steady state, it has to be the unique globally optimal steady state. Now, that's one implication. And the other one, which is a bit more technical, but once one scribbles it down, it's not too surprising. If you presume strict dissipativity, what you get almost for free is that on the infinite horizon, your optimal pair, so Z again is X star U star, so composed state input trajectory, has to converge to this optimal steady state value. Why is that? Well, the storage here has to be bounded on infinite horizons. And now if you think of this functional of an infinite horizon, the integrand has to go to 0. And you can show this only happens if the optimal trajectories converge to the optimal steady state. Okay, these are two implications, but still you might say, hey, I know MPC, I know that we work with terminal constraints and upper bounds on the cost to go. I know how this works. Why should I dig into these dissipativity assumptions? Well, let me try to give you one liner why this is interesting and why it's powerful. When we work with terminal constraints, then we always work with such an integral Lyapunov inequality, that the terminal penalty is an upper bound on the cost to go. When we work with strict dissipation, we work with the inequality here at the bottom of the slide. Now, for both inequalities, I can give you the differential counterparts. The differential counterpart for the Lyapunov inequality is what we all have seen in a lot of papers, is this differential Lyapunov inequality where the decay term on the right-hand side is replaced by our stage cost. And the strict dissipation inequality, I can also write in differential form. And now you can already grasp what the relation between both is. You work with the terminal constraints, you work with upper bounds on the cost to go. If you work with dissipativity, in a nutshell, you work with lower bounds. So you work with lower bounds on the optimal value function. This is specifically the entire change, but you now assume that you know, or that such a lower bound exists globally, not only in a local neighborhood. And so you can summarize this here as dissipativity-based analysis of MPC is just all centered on the idea you want to work with lower bounds on the optimal value function. This would be a one-line summary. But still you might say, hey, I don't like it because I have to assume it. Can I enforce it? Let's go back to our strict dissipation inequality. And I've mentioned before that the strict dissipation inequality holds if the available storage is bounded. Now I want to check the available storage for optimal solutions. What do I have to do? Well, I fix an initial condition, and now I have to check for the largest value of this performance index here, where I plug in as a control function here an optimal control for this initial condition in some horizon length. And now I'm allowed to play with the horizon length. And if for all horizon length, this functional here stays bounded from below, then the available storage is bounded. And then I'm in a good position because I can show that my system is dissipative or satisfies a strict dissipation inequality along all trajectories generated by optimal controls. Now you may say, that's merely technical. It is and it is not. Why is that? The set of optimal controls that are generated by an optimal control problem is something I can influence. I can influence this by the constraints I choose and by the objective I choose. If I have control over my OCP and in MPC design, this is what I will usually have, then I can influence the set of optimal trajectories. And this means nothing else that if you think that's all way too complicated, consider you can reach the origin and you want to track it with MPC, and you would choose your standard LQR like stage cost. Then if you choose this stage cost, you directly have strict dissipativity provided asymptotic reachability holds, and you have it with the storage function being simply the zero function. So the strict dissipativity notion for OCPs, you can say it's a system property, it has to come from my system, or you can say, no. It's actually a property I can enforce by designing the stage cost and the constraints in my optimal control problem. So in some sense, I would say, if you think of it as a kind of design requirement for optimal control problems, then strict dissipativity should not be seen as something too restrictive. Rather, it's something quite natural and quite useful to have. Okay, now, this was my rather long pretext to already convince you that assuming strict dissipativity in an optimal control problem is something natural and not something unusual. Now, let me try to tell you how we turn this into a stability analysis tool which ends up with sufficient and necessary conditions. This is again our continuous time MPC scheme. Let's repeat. We want to stabilize the optimal steady state. And I want to avoid being specific about the choices for the horizon, the terminal penalty, and the terminal constraint. Now, I have three main assumptions that I need besides a few technical things. I assume my strict dissipativity. I assume that my optimal value function is bounded on my, let's say, set of interesting initial conditions, which simply means, okay, on a specific set of initial conditions, my optimal control problem is feasible. Okay, this is what it means. And then I need something which is a bit more technical, because if I look at the MPC closed loop and I plug in here my abstract MPC feedback law, let's denote it by the letter kappa, then due to the recomputation on sample time intervals, this feedback law may jump, it may be discontinuous. So we have some kind of hybrid closed loop here. And now if I assume here some kind of candidate Lyapunov function, I need certain properties of this Lyapunov function. But let me first tell you what enters our Lyapunov function. There's the optimal value function. There's some storage function of our system which certifies strict dissipativity, and we offset the storage function by its value at the optimal steady state. Now, what's the property that we need? Indeed, we need two. We want that whenever the OCP, so our optimal control problem, is feasible, that our candidate Lyapunov-like function is bounded from below, because then we can shift it and assume without loss of generality it's non-negative. That's merely technical. And the other thing is we want that this Lyapunov function is absolutely continuous. If you're not familiar with it, don't worry, you will see it a few slides down the road. But why do we need this? We cannot safely assume that an optimal value function or storage function, that these are continuously differentiable functions. They come from optimal control problems, so there might, at a few locations in the state space, there might be non-differentiable, and we have to account for this. And with the absolute continuity, we somehow have an elegant way out, because we say, non-differentiabilities don't matter as long as our trajectories drive through them and don't stay there. Okay, now, there was our setting. How do we do it? We first have to ask, if we are here in our OCP scheme, and I don't want to specify what's the terminal constraint to terminal penalty, what are commonalities? What's the same no matter what my choice of these design ingredients is? And apparently, one commonality is given by Pontryagin's maximum principle or minimum principle, or by the necessary conditions of optimality. How can you think about it? You take your optimal control problem, And now I construct or I choose a Hamiltonian for this optimal control problem, which involves here some adjoint variable times the dynamics, some extra adjoint for the stage cost, and I want to have here for, let's say, a simplified exposition, something which is called direct adjoining in optimal control. So some multiplier times the mixed input state constraints. Also need some technical regularity assumptions where I spare you the technical details. Now, if we do that, we can write down the P&P for this problem. What we have here is the state dynamics along optimal trajectories are given by the gradient of the Hamiltonian with respect to lambda. The adjoint dynamics are given by minus the gradient of the Hamiltonian with respect to x. We also have the usual minimization of the Hamiltonian, and due to the fact that we have adjoint the constraints here to the Hamiltonian, we also get a kind of stationarity of the Hamiltonian with respect to u. And this extra multiplier function mu has to satisfy here some standard complementarity condition, which most of you will have seen if you wrote down KKT conditions. And there are some other conditions which I have left out here because these are the main ones that we need in the following. Now, that's the P&P. And we can ask, so what does now change in there if I play around with the horizon, with the terminal penalty, or with the terminal constraint set? And indeed, not much, because what mostly changes is the boundary condition of the adjoint. That's the usual thing that will change. But the structure of the optimality system as such, in terms of state and adjoint dynamics, will not change. Also, the requirement of minimization of the Hamiltonian. Moreover, no matter how I choose my design ingredients, at points of differentiability, standard textbook knowledge, the gradient of the optimal value function will equal the adjoint, which is something very handy. And due to the specific structure of the optimality system, the Hamiltonian is constant along optimal solutions. Why is this the case? Well, if you compute the full differential with respect to time of the Hamiltonian, you get its partial with respect to time, then the variations with respect to x, lambda, and u. These two terms you can directly see there is 0 because we have a time invariant problem, and the gradient of h with respect to u is 0. And these two terms in the middle, they cancel each other out precisely due to the skew symmetric structure that we have up here. And now, what's the main message? If you write down the P&P, well, its structure doesn't change so much except for the terminal condition of the adjoint, depending for terminal ingredients that you put there, like terminal penalties and terminal constraints. And crucial fact, the Hamiltonian is constant along optimal trajectories in a time invariant setting. And this constant Hamiltonian is what we're going to exploit next. Because I've already used it in this talk, and all of you will be familiar with it, the optimal value function is something incredibly smart, right? Because it maps the initial condition of an optimal control problem to the value of its performance index after optimization. So if there are multiple optimal solutions, well, they're somehow hidden in how you choose an optimal solution, but they don't change the value of the optimal value function. And now, inspired by this, we make here a similar definition. We consider what we like to call the receding horizon Hamiltonian. It takes the initial condition of the OCP and maps it to the value of the Hamiltonian, okay? And what do we know that? Well, as long as an optimal control exists, this Hamiltonian will be well-defined. For each initial condition, so for each OCP that I solve on the language of predictive control, for each prediction, it will be a constant number. However, it will change from prediction to prediction, right? If I change the initial condition, I get a different optimal solution, and I will get a different value for the Hamiltonian. Now, what can we do with this receding horizon Hamiltonian? A simple observation. Again, let's take a look at the NMPC closed loop. And let's suppose it converges to some equilibrium. Let's call it x tilde. What happens if the MPC closed loop converges to an equilibrium? Well, it the corresponding MPC feedback should go to some utility such that f of x tilde utility is 0 because it's in equilibrium. But if f of x tilde utility is 0, then the Hamiltonian will also have a dedicated value. Namely, it will correspond to the stage cost at this equilibrium x tilde utility. That's easy to see. You just take the Hamiltonian, you assume, okay, I am at steady state in my MPC loop. Then this term vanishes due to the system being at steady state. This term vanishes due to complementarity slackness. And then you assume something which in optimal control slang is called that this problem is not abnormal. And there you have it. You have a simple value of the receding horizon Hamiltonian. So somehow this means that the receding horizon Hamiltonian gives us a kind of indicator for convergence of the closed loop. But of course, that's not very deep. We should do a bit more here. And there we need, I know it's a technical talk, I need one more technical thing, simply due to the fact that I have don't want to recompute at each point in time, but I have a sample data in nature. And in between two recalculation instances, I want to apply an optimal control in open loop. And what I need to account for in between these sampling instances, tk plus 1, is the change of the adjoint coming from our open loop prediction compared to what would have happened if I would have re-optimized. It's a bit technical. But I just collect this here in this abstract function, delta, which just accounts for, okay, how much does the adjoint variable vary before I re-optimize? Now, if I do this technical definition, take my three assumptions, and then suppose that these expressions here, which account for the re-optimization, stay bounded, then the closed MPC loop converges to an optimal equilibrium if and only if the following three conditions hold jointly. At the optimal steady state, I want my receding horizon Hamiltonian to be 0, why 0? Because just for sake of normalization, I've assumed at the optimal steady state, I want my stage cost to be 0. Could have written this differently, but this makes our life a bit easier. Naturally, follows directly from our previous considerations, the receding horizon Hamiltonian as a sequence has to converge to its optimal steady state value for the closed loop to converge. And this is not enough. I also need that the sequence has to converge sufficiently fast, saying that it has to be a summable sequence. It cannot take arbitrarily long for convergence. And if we have these three things, I will try to convince you that this is not only sufficient, but also necessary. How does the proof go? We start off with exploiting that our candidate Lyapunov function is absolutely continuous, which means I can always write its evolution by this integral equation. And here its full differential with respect to time appears. Now the trick with absolute continuity is W dot doesn't need to be well defined. At a few instances in time, it can be undefined as long as the integral exists. Now we compute W dot, the usual derivative. We plug in our strict dissipativity. And that's what we have at each sampling instance. Namely, here from the strict dissipation, we get this minus the class K function, which is nice, which we will need to ensure convergence. And what we have here is nothing else than the value of our receding horizon Hamiltonian. Why is that? Well, because the gradient of the adjoint corresponds, the gradient of the optimal value function corresponds to the adjoint variable. So there our Hamiltonian reappears. And now you can already grasp what is going to happen. We will now take a look at how this term here changes over the different OCPs we solve. But this inequality only holds at a sampling instance. Now we also have to take care of the intersampling effect. So what happens between tk and the next sampling instance tk plus delta. And this is where this nasty expression here for the sampling effects comes into play, which describes nothing else that the adjoint variables will change slightly until I re-optimize. Okay, now that I have this, what can I do with this inequality? I can integrate it from 0 to infinity. And if I do so, well, it's not too bad, because since my receding horizon Hamiltonian is always constant for each let's say, sampling interval, I can simply turn this into a sum. Here we have an integral over our class K function, and here we have this term which accounts for the sampling effects. Now, exploiting that my candidate Lyapunov function is bounded from below, I can reshuffle terms, such as to make here this integral over the class K function appear on the left-hand side. And now what I have required from my series of the receding horizon Hamiltonian and of these terms capturing the sampling effects is nothing else than that this sum on the right-hand side is bounded. And this allows me to apply Barbalat's lemma. And voila, I have a convergence result. So then it has to converge. It's just rearranging the terms. That goes very nicely. But that's sufficiency. What about the necessity? Just a quick sketch here. We can assume two situations. The receding horizon Hamiltonian converges to a non-zero value, or it diverges. Now, let's assume it converges to a non-zero value, which corresponds to some other steady state. Then strict dissipativity allows me to conclude, well, that at the optimal steady state, the stage cost vanishes, and if the receding horizon Hamiltonian converges somewhere else, I cannot be at the optimal steady state. That's the one direction. Now, the other direction is the sequence doesn't have a limit, but the closed loop converges. That's a bit the brain twister, but if this would happen, well, this would contradict our observation that we have made before. Whenever the closed loop goes to a steady state, the receding horizon Hamiltonian has to take on a constant value, right? And there you have a contradiction. That's why these conditions looked at jointly are also necessary for convergence. Okay, that's all very technical. You can say, hey, that's not so easy and definitely not easy to grasp in a presentation. What do you do with it? How do you make use of this results in a if you look at a system? Taking here a chemical reactor with two reactions, actually three reactions going on. What are my controls? The volume flow through the reactor and the temperature and the cooling jacket here. And if I derive a partial model of this reactor, I have three state variables. They're highly nonlinear. And what do I want to do? I want to maximize the amount of product B. This is what I want to produce in this reactor. And this can be expressed by this stage cost here, which I normalize because that's a singular problem. So I want to improve its numerical solution structure. So I add a small regularization. Why have I picked this example? Because in previous publications, we've shown that it's nicely controllable in the presence of constraints and that this OCP is strictly dissipative. And I simply now solve this optimal control problem in receding horizon fashion with some standard tools, Casadi and the Runge-Kutta fourth order scheme, some fixed step size, and see what happens to my Hamiltonian values. How do I compute the Hamiltonian values? Well, I simply say I take the dual information out of my NLP solver, namely the Lagrange multipliers for the dynamics and the Lagrange multipliers for my constraints, and plug them into my formula for the Hamiltonian. And then I want to see what happens. And I pick these dual variables in the middle of the horizon. So that's the first scheme I look at. I use here a terminal constraint at the optimal steady state, no terminal penalty. I've plotted you here, I think, 5 initial conditions. The red line is the optimal steady state. And as you can see, the states here converge nicely. U2 converges nicely. Why haven't I plotted U1? Because it always stays at its upper limit all the time, so we don't need to plot it. This now is the sequence of the Hamiltonian plotted over my sampling instances for the different initial conditions. And you see it also converges very nicely to its optimal steady state value. And indeed, it does so sufficiently fast such that the series is summable. That works very nice. Now we slightly change the problem. That is, we remove the terminal constraint. And then you can show in this setting, you can only expect that you steer close to the optimal steady state. And this is precisely what happens here in our closed loop simulations. And on purpose, I've picked here a very short horizon such that this distance here is really nicely visible. And what now happens is, of course, my receding horizon Hamiltonian convergence to a non-optimal value. And if I sum over its values, if I sum the sequence up, well, then it grows with a certain linear rate and doesn't converge to sum here. And that's why, or that's very much in line with our predictions that this system does not converge to the optimal steady state. Now we increase the horizon, make it longer, then the distance to the optimal steady state becomes smaller. And this is indeed what you can observe here. Now our sequence is converging much better here in terms of it's not growing that fast, but still it doesn't converge. And the difference you can nicely see here in terms of the numerical values. Okay, now a fourth or third variant depends on how you count, where I apply a linear end penalty. Oops, that's not what should happen. So where I apply a linear end penalty, whereas this linear end penalty coming from, at the end of the day, this is a linear approximation of my optimal value function at steady state. And there again, we could show in different paper, this has to converge, but again, this fits to our conditions here. The receding horizon Hamiltonian converges, and as does this sum over the values of the receding horizon Hamiltonian. So that works all very nicely. So looks like really interesting and something we can work with, but where's the grain of salt you should be looking for? And what one potential grain of salt is the fact that I would claim about 90% of all papers published in MPC will focus on the discrete time case, and also a substantial amount of implementations will take a discrete time point of view. So what happens if we try to bring this to the discrete time world? And at first glance, you say, hey, this should be somewhat possible and doable because a discrete time OCP and a continuous time OCP, at the end of the day, they're not too different. Specifically, if we take a discrete time OCP, and now we compute a pointwise in time Lagrangian, so at each point on our horizon, we take the stage cost and then adjoin the equality constraint for the dynamics to it and further equality or inequality constraints here. And then we sum these pointwise in time Lagrangian, compute Lagrangian stationarity, so nothing else than KKT conditions. And if we look at this from the right angle, then what we get is here our dynamics. We get a backward recursion for the Lagrange multipliers for the equality constraints imposed by the dynamics, and we get a stationarity of this Lagrangian with respect to the control input that is somehow we have to optimize with respect to u. So that looks all nice and good, especially if we write down our continuous time optimality conditions once more, namely we spell it out, these partials with respect to the Hamiltonian, then we have here the dynamics, we have here the adjoint equation, and we have here our stationarity condition. And now if you look at it, the backwards in time recursion we have for discrete time is reflected here by the minus sign. So there's a lot of structural similarity. And on the left-hand side, in continuous time, we have that the Hamiltonian is constant, which motivates the question, is the Hamiltonian going to be constant in the discrete time setting? And what is the Hamiltonian I'm going to look at? Well, the usual one, you take the stage cost times Lagrange multiplier times the dynamics plus Lagrange multiplier times the further inequality constraints. And what we do is we solve one open loop OCP here out of our sequence, arbitrarily chosen. We compute the Hamiltonian from the discretized primal and dual OCP solution. So we take the states and the controls and the dual variables of the discretized OCP solution, so of the NLP we solve, compute the Hamiltonian, and then to compare, we also post-integrate the states and the adjoint variables on a very fine grid, here with a variable order step size integrator just to double check. And what you see here in the plot are the different state variables Blue is the directly the result taken from the optimizer. Red or orange dashed is the post integration. And now you see it matches very nicely for the states, and for the joints, only small offsets seems to look very good. The bad news is if I plug it into my Hamiltonian, this is what happens. The Hamiltonian, if you compute it on dual information from the NLP solver, is not constant. Now you could say, hey, either it's due to your NLP solver or there's a fundamental thing. So we take more steps, increase the horizon, and what we see here, the offset becomes smaller, the difference, but still the Hamiltonian is not constant. If we take it directly from the NLP solver and we crank it up even more, taking here 2,500 steps on a rather short horizon, and now you see whatever I do, I can't manage to get that Hamiltonian to be constant. However, in the middle of the horizon, it matches the continuous time value very well, the discrete time information, but not at the ends of the horizon. So what is going on there? And matter of factly, if you write down the discrete time Pontryagin maximum principle, you do not have that the Hamiltonian is constant. For a long time, I was always thinking, why has now no one written it down? Until I figured it out, no, it cannot hold. And this is due to the fact that some parts of the Hamiltonian structure, which preserve, so to speak, the energy or which keep the Hamiltonian constant, are lost in discrete time, surprisingly. And that is also something you can rigorously show. And on top, there comes something that a lot of the codes we use to solve OCPs are not tailored to give us precise dual information. That also comes on top. So at this point, you might say, hey, let's take these roughly 44 slides, let's throw them to the bin and say, if we can't make it work in discrete time MPC, what should we do with it? But it's not that easy. Because you can think about where can I compute the Hamiltonian without needing access to my adjoint variables, without needing dual information. And if you look at this formula here, and I've replotted you here one of the long horizon solutions, then you will observe in the middle of the horizon, the solutions stay roughly constant. This is not a coincidence. This is induced by the strict dissipativity we have underlying, because there's a kind of turnpike phenomenon going on, which means the middle of the horizon, the dynamics are almost at steady state. And that is why in the middle of the horizon, these terms here, which depend on dual information, these ones, will cancel to zero, and I don't need to know the dual information. At the same time, what our previous analysis has shown numerically is that in terms of primal variables, inputs and states, my predictions out of the discretized program are quite accurate. They're not too bad. Otherwise, the post-integration should have failed. So it's really the dual information. And there are two more options what you can do. You could go to the end of the horizon if you have a terminal constraint, or you invest the extra numerical effort to integrate the optimality system just a tiny little bit backward in time with high accuracy. Then you also get the value of the Hamiltonian very accurately. So you can get it, and you can even get it without using the dual information out of your NLP solver. There we have to be a bit careful. Now, let me sum up. Time's up. What have I tried to show you? I've tried to, let's say, steer up a discussion on whether in analyzing MPC schemes, we can do more than just another set of sufficient conditions. Can we do something which is sufficient and necessary? The point of view I've taken here is centered on the PMP that is on the receding horizon Hamiltonian, precisely. So analyzing an MPC loop by looking at how the Hamiltonian changes over the MPC sequence. If you have looked sharply, then on the main result, I've very bluntly assumed recursive feasibility. You might say, hey, that's a strong assumption. Can't you get rid of it? Yes, we can. Under the conditions we have imposed here, we could show that there exists a sufficiently long horizon where recursive feasibility is not an issue, or you could simply tweak our stability conditions by saying, whenever the OCP is infeasible, I assign the value infinity to the Hamiltonian, and then the summability of the sequence directly implies recursive feasibility. So that's not a big deal. Now you may wonder how to check the conditions. And my take on this is, first, a slightly provocative question asking, are MPC stability conditions ever checked? I publicly admitted here, when we implemented it, we checked in simulation, but didn't write down terminal constraints and terminal penalties to make it work on the real world system. We could simply get away with sufficiently long horizon. And I would claim that this is what really happens in practice, where what I've shown you here is somewhat nice because you can check it at the runtime of the controller in an automated fashion. And this also pays where I think we can go from here, namely talking about what is automatic controller tuning, not tuning them by hand, but doing this automatically. Now, what are future work? I've started off with asymptotic stability, but I've only shown you asymptotic convergence. This is a gap which we should address. If you look very careful in what we did, it hinges on the structure of the optimality system, not so much on optimality. So it should work in a suboptimal case. We already know it works for distributed MPC as well, but there is an unexplored link to the Hamilton-Jacobi-Bellman equation. Yeah, and that's what keeps us busy. And with this, I'd like to conclude. I'm very happy to take questions, feedback, and comments.
Thank you very much.